Good morning, students. This is the next topic in D block elements, that is characteristics of transitional elements. First property is they exhibit variable oxidation states due to less energy difference between ns and n-1d orbitals. That means what? These elements exhibit more number of oxidation states because the energy difference between outermost orbits, that is ns and n-1d orbitals, is very less. If energy difference is very less, automatically the electrons present in those orbits will involve in chemical reactions when those elements react with other substances. So that is the meaning of that point. For example, take scandium. Scandium atomic number 21. Its electronic configuration argon 4s2 3d1, 4s3d. That means ns n-1d. In case of scandium, that means when scandium reacts with any other substance, then the electrons present in ns and n-1d, nothing but 4s and 3, those electrons involves in reaction. Because the energy difference between 4s and 3d is very less, so automatically all those electrons involves in reaction. If all electrons involves in reaction, automatically oxygen states will increase. That is the meaning of that point. In case of titanium, chromium, manganese, copper, zinc, in all cases same thing takes place. That is the first point. Second point, all are hard metals, so they have high melting point and boiling point. Next point, they exhibit catalytic properties. That means they act as catalysts. Most of the transitional elements act as catalysts in chemical reactions. For example, take Haber's process. In that Haber's process, what is the catalyst? Iron. And take contact process. In that contact process, which is catalyst? Vanadium pentoxide or platinum. Platinum is a transitional element. Vanadium, nothing but vanadium pentoxide, nothing but that is the transitional metal oxide. Next, they exhibit color in aqueous solutions. That means when they are present in solutions, they exhibit color. Next, they exhibit magnetic behavior. That means whether they are paramagnetic, diamagnetic, ferromagnetic. So these are the properties of magnetic behavior. So these elements exhibit magnetic behavior. Next, they form alloys with metals and non-metals. Next, they form interstitial compounds. We will discuss later about this one, then you get idea about this one. Next, they form complex compounds. Next, they exhibit conductivity. Conductivity means when we pass electricity to these substances, that means to these transitional elements, then they exhibit conductivity. That is the meaning of that point. Next, they have properties like malleability and ductility. Malleability means making of sheets. Ductility means making of wires. That means by using these elements, we can make sheets and wires. That is the meaning of this point. For example, gold. So gold is a stable metal. Even though it is stable, by using gold we can make rings, chains. So that is the example for malleability and ductility. So all these are what characteristics of transitional elements. Here we have to know one more point, that is here we have to discuss each and every characteristic transitional elements separately. Then automatically this chapter will be finished. Especially this topic is there, complex compounds, that is separate next chapter. That is the next chapter. We have to discuss each and every topic later. Next, atomic size. One more name is atomic radius. That means we have to discuss atomic radius of transitional elements. We know that in periods from left to right, atomic radius gradually decreases. So in this case also atomic radius decreases, but the atomic radius decreases from scandium to manganese, and it is same in iron, cobalt and nickel. Scandium, after scandium, titanium, after that vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the elements which are present in 3D series. Now I am discussing about atomic size regarding 3D series. So what is the point here? From scandium to manganese, atomic radius decreases as we expected, but it is same in iron, cobalt, nickel. That means at the middle of the transition series, the atomic radius is same. It is due to same nuclear attraction. That means in those three cases, nuclear attraction is same. That is why atomic radius will be same in those three cases. Next, but from copper to zinc, it slightly increases due to repulsions between paired electrons in their valence shell. This is also very important point. See, copper outer electronic configuration is what? 4s1 3d10, and zinc 4s2 3d10. In that case, compared to copper, zinc having more number of paired electrons. If paired electrons are present, automatically between the paired electrons some repulsions occurs. If repulsions occur, automatically the atomic size somehow increases than expected. So that copper is having less atomic size compared to zinc. Zinc is having more atomic size compared to copper. Next, in groups from top to bottom, the atomic radius gradually increases. We know that due to increasing number of shells. So compared to 3D series, 4D series having more atomic size. So from 3D to 4D, the atomic radius increases. But in case of 4D and 5D, the atomic radius is similar. This is somehow important point, and one of the important point. In case of 4D series elements, they are having more atomic size compared to 3D. But in case of 4D and 5D, the atomic size is same due to lanthanoid contraction. See, zirconium, this is 4D series element, but osmium, this is 5D series element. Below zirconium, osmium is present. As per theory, osmium should have more size compared to zirconium, but both are having same atomic size due to lanthanoid contraction. In case of this pair also, niobium, this is belongs to 4D series, but tantalum, this is belongs to 5D series. Actually, tantalum should have more size, but both are having same atomic size due to lanthanoid contraction. In case of this one also, molybdenum is belongs to 3D series, sorry, 4D series. Tungsten, W means tungsten, that is belongs to 5D series. So what is the point here? What is the point? The atomic radii of 4D and 5D is similar due to lanthanoid contraction. This is here graph is drawn between atomic radius and atomic number. See, this is 3D series, 4D series, 5D series. We need not discuss about 6D series because that is incomplete period. So what we discussed regarding 3D series, from scandium to manganese, atomic radius gradually decreases as we expected, but from iron, cobalt, nickel, atomic radius will be same. That is why here this center line indicates those elements. That indicates what? They are having same atomic radius, but from copper to zinc it slightly increases. That is the meaning of that point. Next, from in case of 4D and 5D, we drawn the lines side by side. That indicates what? Both are having same atomic radii due to lanthanoid contraction. That is the meaning of these three curves. This is about atomic radii of d block elements. nothing but transitional elements. Next, ionization potential. We know that if atomic size increases, ionization potential decreases. In 3D series elements, zinc has more IP. Why? Because zinc having outermost configuration of 4s2 and 3d10. That means all are having paired electrons. And 3d10, that means nothing but completely filled configuration. So that it will be more stable. Because it is very difficult to remove the electron from stable configuration elements. Next, in case of 4D series, cadmium has more IP because below zinc, cadmium is present. Below cadmium, mercury is present. In case of 5D series, mercury has more IP. But in all D block elements, mercury has high IP. In all D block elements, mercury has high IP. This is very, very important point. Here, you have to know one more point. That is zinc, cadmium, mercury. These three elements present in same group, that is 2b group. But from top to bottom, what happens? Atomic size increases, thereby IP decreases. Thereby, mercury should have less IP, but mercury has more IP. This is very important point because compared to zinc, here zinc atomic number 30, cadmium 48, mercury 80. That means compared to zinc, mercury having more atomic number, and here effective nuclear attraction will be more. Effective nuclear attraction will be more. If effective nuclear attraction will be more, then size will be less than expected. Then automatically IP will be more. That is the reason behind that one. I repeat that point once again. Compared to zinc, that means from top to bottom, this effective nuclear attraction will be more in case of mercury. Thereby size will be less than expected, so that mercury will be high IP. So this is a very important point. Next point regarding melting points and boiling points. In D block elements, if number of unpaired electrons, see this is the point regarding melting point, boiling point. In D block elements, if number of unpaired electrons, not paired electrons, increases in their valence shells, then melting point, boiling point also increases. For example, take chromium. Chromium atomic number 24, its electronic configuration 4s1 3d5. That means it contains 6 valence electrons. In case of manganese 4s2 3d5, that means it contains 5 valence electrons. In that 3d series, no element having that much unpaired electrons compared to chromium and manganese. Chromium having 6 unpaired electrons, manganese having 5 unpaired electrons only. So that chromium has more melting point than all elements which are present in 3D series. That is very important point. Why chromium having more melting point in 3D series? You may face such type of question for 1 mark in CBSE level. So what is the answer? Chromium having more number of unpaired electrons in its valence shell. If number of unpaired electrons increases in valence shell, then their melting point, boiling point increases in case of transition elements. Next, see in 3D series, chromium has more melting point and zinc has low melting point. Why zinc has low melting point? Because in zinc there is no unpaired electron. There is no unpaired electron. Automatically it will be having less MP. Next, in 4D series elements, cadmium has low melting point. Cadmium, because below zinc cadmium is present, and in 5D series mercury has low melting point. In 5D series, because below cadmium mercury is present. Next, here see, this is not magnesium, you just correct it. This is manganese. Manganese and technetium. Tc means technetium. Manganese and technetium have low melting point even though they are having more number of unpaired. This is exceptional point. Manganese and technetium having more number of unpaired electrons even though they are having, so manganese and technetium have low melting point even though they are having more number of unpaired electrons. That is due to difference in their crystal structures. This is also one of the important point. What is the point? What is the reason behind that one? Manganese and technetium. Below manganese, technetium is present. Both are having low melting point even though they are having more number of unpaired electrons. That is due to difference in the crystal structures. So this is all about MP and BP of transition elements. Next topic, oxidation states. This is the first characteristic. They exhibit a more number of oxidation states due to less energy difference between N-less and N-1D substrate C. Here only outer electronic configurations is mentioned for corresponding elements. C is scandium 4s2 3d1, titanium 4s2 3d2, vanadium 4s2 3d3, chromium 4s1 3d5, manganese 4s2 3d5, iron 4s2 3d6, cobalt 4s2 3d7, nickel 4s2 3d8, copper 4s1 3d10, and zinc 4s2 3d10. See, in case of scandium, it exhibits only +3 oxidation state. That means when scandium reacts with any other substance, these 3 electrons usually involve in reactions. We can't say why scandium exhibit not exhibit +2, not exhibit +1. That is we can't say because these are experimental factors. Next, in case of titanium, it exhibits +2, +3, +4. That means it exhibits these 3 oxidation states. Vanadium, it exhibits +2, +3, +4, +5. It exhibits 4 oxidation states. Chromium exhibits +1, +2, +3, +4, +5, +6. It exhibits these oxidation states. Manganese, it exhibits +2, +3, +4, +5, +6, +7. It exhibits more number of oxidation states. So in case of iron, it exhibits +2, +3, +4, +6. In case of cobalt, it exhibits +2, +3, +4. In case of nickel, it exhibits +2, +3, +4. In case of copper, it exhibits only 2 oxidation states. They are +1 and +2. But zinc exhibits only 1 oxidation state, that is +2. Here one important point is that is which transitional element, listen carefully, which transitional element does not exhibit variable oxidation state? What is the answer? Scandium or zinc? For that answer is scandium, because zinc is not transition element, it is d block element. What I asked you, which transition element? So that answer is scandium. It exhibits only 1 oxidation state. Suppose if the question is which d block element does not exhibit variable oxidation state, if the question is like that, then what is the answer? Zinc. Next, one more point is what? Here, all these cannot be explained theoretically. That means why manganese exhibits these number of oxidation states, why zinc exhibits only these oxidation. We cannot explain. All these are experimental factors. You just know it. No need to remember these oxidation states. You just know it. Next, the main important point here is the common oxidation state of d block elements is +2, except scandium. Every element exhibits +2 oxidation state, so that it will be common oxidation state. Next point, the lower oxidation state is due to the involvement of Ns electrons. The lower oxidation state is due to the involvement of Ns electrons. See, in case of titanium, what is the lowest oxidation state? +2. That means if 4s2 electrons involves in bonding, then it exhibits +2. In case of vanadium, what is the lower oxidation state? In this case also +2. That means in these 4s2 electrons involves in bonding, then it exhibits +2. In case of chromium, what is the lower oxidation state? +1. That means when these electron involves in bonding, then it exhibits +1. So in not only in this case, in every case except in scandium, in every case the lower oxidation state is what? due to involvement of ns electrons. Next, from scandium to manganese, that means from here to here, the higher oxidation state is due to the involvement of ns and n minus 1d electrons. What is the point here? Higher oxidation state, that means in case of scandium, this is the only one oxidation state. So that is in formed due to involvement of ns and n minus 1, 2 plus 1. In case of titanium, plus 4, that means 4 is to 3 to 2, that means 4. In case of vanadium, plus 5 is the highest oxidation state, that means when these electrons and these electrons involves in bonding, then it gets plus 5. In case of chromium, when these electrons and these electrons involves in bonding, then it gets more oxidation state. In case of manganese also, when these electrons and these electrons are involved in bonding, then it exhibits plus 7. So that is the meaning of that point. From scandium to manganese, the higher oxidation state is due to the involvement of ns and n minus 1d electrons. Next, scandium is the only transitional element which does not exhibit variable oxidation state. I discussed already. Next, in 3D series, manganese exhibit more number of variable oxidation state. You just remember this point. In 3D series, manganese, that means it exhibits more number of oxidation state. Next, in 3D series, the highest oxidation state is exhibited by manganese, because see, this is plus 1, so the rest of the elements exhibit plus 4, plus 5, plus 6. So which element exhibit more number of oxidation state? Manganese. And which element exhibit highest oxidation state? Manganese. So for the two questions, answer is same. What is the answer? Manganese. Next, the highest oxidation state, this is important point. The highest oxidation state in d block elements is plus 8. Which elements exhibit plus 8? Ruthenium, rhodium and osmium. Ruthenium, rhodium and osmium, these are the elements which exhibit highest oxidation state in d block. Next topic, stability of higher oxidation states. The d block elements exhibit higher oxidation states in oxides and fluorides. This is one of the important topic. So what is the point here? D block elements exhibit higher oxidation states in case of their oxides and fluorides. That means when these elements react with oxygen and fluorine, then only they exhibit higher oxidation states. Not more number of oxygen, higher oxidation state. The stability of oxides is that means in case of oxides, the stability of oxides is due to multiple bonds formed by oxygen. That means when these elements react with oxygen, then these elements exhibit higher oxidation state. That is okay. Then what is their stability? Oxygen forms multiple bonds with transition elements. Then they get more stable. That is the meaning of that point. Next, in case of fluorides, the stability is due to lattice energy or high bond dissociation energy. That means when these elements react with fluorine, they form fluorides, but their stability is due to lattice energy. That means between fluorine and the transitional elements, the bond is very strong. That means it needs more energy to break that bond. That is due to lattice energy. Next, one more point. This is also important point. Cu2 does not exist. CuCl2 exists, CuF2 exists, but Cu2 does not exist because this iodide, I minus means iodide. I discussed all these points: fluoride, chloride, bromide, iodide in 17th group elements. In all these iodides, fluoride has more oxidizing power, but iodide has more reducing power. So in Cu2, iodide has more reducing power, so it reduces immediately Cu plus 2 to Cu plus 1. So it does not exist. I just repeat once again, this is very important. One more question: why Cui2 does not exist? What is the answer? In case of Cui2, iodine having -1 oxidation state, since it has more reducing power. Reducing power means what? Tendency to give the electrons to copper, not only copper, other substance. Then automatically the oxidation state of copper reduces from +2 to +1. In this case, copper having +2. Immediately, if oxidation state decreases, automatically Cu(I2) becomes Cui. That means Cui2 does not exist. So that is the reason behind that one. Similarly, Fe(I3) also does not exist. What is the reason? In case of Fe(I3), iodide having more reducing power, it reduces Fe plus 3 to +2. So Fe(I3) does not exist. So this is also one of the important question. Next, here one more important question. This is very important question. See, why Cr plus 2? Cr plus 2. What is the electronic configuration of chromium? Electronic configuration of chromium is 4s1 3d5. Cr plus 2 means 4s0 3d4. That means we have to remove 2 electrons. Next, what is the electronic configuration of Mn plus 3? Mn 4s2 3d5. 4s2 3d5. We have to remove 3 electrons. That means 4s0 3d4. That means Cr plus 2 and Mn plus 3 both are having d4. That means 3d4 configuration. So what is the question here? Why Cr plus 2 acts as reducing agent and Mn plus 3 acts as oxidizing agent, even though both are having same configuration? What is the meaning of reducing agent? Tendency to lose the electrons. What is the meaning of oxidizing agent? Tendency to gain the electrons. So both are, even though both are having same electronic configuration, why it acts as like this? Why it acts as like this? That is the meaning of the question. So what is the answer? In Cr plus 2, if Cr plus 2 loses electrons, then configuration changes from d4 to d3. Correct. In that configuration, d2g orbitals are off-filled, so it acts as reducing agent. That's all. See, here you have to know one more point. D orbitals is split into 2 groups, T2g and Eg. T2g having 3 orbitals and Eg having 2 orbitals. So what is the point here? If Cr plus 2 loses electrons, then its configuration becomes d4 to d3. Then that T2g orbitals become off-filled. If an atom having off-filled or completely filled, that will be more stable. If an atom or ion, anything. So when it loses electrons, it becomes stable, so that it acts as reducing agent. That is the answer. That is the reason behind that one. In case of Mn plus 3, if Mn plus 3 gains electrons, then its configuration changes from d4 to d5. d4 to d5 means d5. That means all d orbitals having one unpaired electron. That means it is off-filled configuration. That means it is also stable. That means in case of Mn plus 3 also, stability configuration takes place when it gains electrons. That is why it acts as an oxidizing agent. So this is very important question for 1 mark. So this is about transitional elements. There are some more points. We will discuss those points in next class. Thank you.